Hi, I'm Sala, and in this video we are going to discuss the recursive version of the Bayes formula for the hidden tiger case study we were discussing in previous videos. Basically, we had a zookeeper behind some opaque doors, and then we had a tiger wandering left and right until the central gate closed, so he will be in either side with some given prior probability, and then we acquire information from the roaring on where the tiger is. The accuracy of my measurements, let's say, is governed by this conditional probability table, so that if tiger is left, I listen most of the times, say 80%, through the left door, the roarings, 20% at the wrong door at the right hand side, and if the tiger is at the right hand side cage, I can hear 90% of the times roaring events at the right hand side door and 10% at the wrong door. So with this conditional table and the prior belief, I can build a joint probability table and recover marginals, conditionals, and whatever. In particular, if we have this conditional table and the prior belief on tiger being right denoted by lowercase b, I can apply Bayesian formula to give me the posterior probability of tiger being right, given that I actually heard tiger roaring at the left-hand side door, in which we use this row of the conditional to form the joints multiplying by b and 1 minus b, the belief on tiger right or left. And on the other hand, if I do listen to a single roaring event at the right hand side door, then I would use the second row, which is the one related to actually observing here right event conditioned to the two possible tiger states. Then, if we assume conditional independence, so that one roaring event, if the tiger doesn't change side, is independent of previous roaring events, then we can multiply conditional probabilities. So for instance, we crafted these two roaring combinations, the observing left, 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 right, right, left, right, right, with this conditional table, so that I would apply Bayes' formula with whatever event I observe. Let's say if I observe left, right, then using this times b and this times 1 minus b, I can apply Bayes' formula. And we also did it for an arbitrary number of roarings, in which I grouped all permutations having the same number of lefts and rights, so I used binomial coefficients. So I will have this 3 roaring table, or this conditional probability table only discussing when I hear m roaring events at the left door and n roaring events at the right hand side door. So with this I would apply Bayes' formula. But well, the thing is that we can achieve equivalent results with what is called the recursive Bayes formula. Let's see it first for 2 roaring events and then for an arbitrary number. So let us recall this conditional probability table and assume that, for instance, we listened to a first left roaring event. So we want to trace back the probability of tiger left or tiger right locations posterior to actually hearing the left roaring. Then this is Bayes' formula when b is the prior on tiger right. And then we can assert the following conjecture. The conjecture is, let us imagine that I plug this b after the first left roar as a prior, and then I apply again this probability table after hearing a second roar that, for instance, maybe it's again 2 left roarings in a row. Well, in this case, I will just apply the same Bayes formula, but replacing the prior zero roarings with the prior before two roarings but after the first roaring. So the issue is that, will this give me the same posterior result to what I would obtain applying this two roaring table with the left event and prior b, 1 minus b? Well, it happens that it indeed is true. Let us prove it, and then we'll move on to proving that general case. Because indeed, if in this formula I replace in b plus that expression, then I get this. And now, if I multiply numerator and denominator by this thing, I remove them, and I have r squared b, and in here again r squared b, and down here q squared 1 minus b, which indeed coincides with the application of Bayes' formula for this left observed event in the non-recursive way. So it seems that it's the same applying twice Bayes' formula using as prior the last posterior that applying once Bayes' formula with the non-recursive two roaring conditional table. Then will this happen in a general case? Well, under conditional independence assumptions, the answer is yes. Let us state and prove that main result. Let us assume that I have a set of past observations, left, right, left, on here in which side the tiger roars, and then I will symbolize that set of past experience with capital O subscript capital N, and then I will assume that I get a new observation, lowercase o subscript n plus 1. Then let us imagine that somebody computed this posterior probability, posterior to listening to capital N roaring events, and let us assume that I use that posterior as the prior in the subsequent application of Bayes' formula with a single event. This is lowercase, this is a single event. So for instance, if O n plus 1 lowercase had been here left, then because the conditional was like this, then if I here left, I would think in this row of the single roaring table, so this will be, let's say, R, and this would be Q. So well, the thing is that if I use the single roaring conditional table with the prior given by the posterior of the past observation, then will this be the actual posterior probability I would have computed with the non-recursive table in here? The result is yes, under conditional independence assumption, under the assumption that the next observation, lowercase o, the side we hear the roaring event, we'll assume that it is independent of the past observations, conditioned to tiger being at the same side. So that's why we call that conditional independence. So we needed that assumption to write this table, and we do need that assumption to be able to chain the applications of the Bayes formula. So let us prove it in a very similar way to the two roaring event stuff. The basic idea would be, let us replace this into this, and of course also in the denominator, and then let us simplify the resulting fraction and see what happens. I plug this in there, so I get this stuff, and well, in here I use the fact that, you know, the applications of Bayes formula is something like y divided by y plus z. So you can see this would be y and this would be z. I have one joint probability, and the marginal is that joint probability plus some other stuff from the joint table. So 1 minus this stuff is this expression that ends up being z over y plus z. So, well, I put z in there, so I get this expression in order to compute 1 minus all that stuff. So good. Then I have replaced the prior by the Bayes formula with the non-recursive table of with whatever expression we made to compute this. And now, if I remove denominators by multiplying everything by this, then I get this product of conditional probabilities times the no roaring prior, and same here, and this product of conditional probabilities times the belief before listening to any roaring event. Then we end up with this expression, and now we are going to use my conditional independence assumption, saying that, well, if the next observation is statistically independent from previous one, if tiger does not switch side, then okay, tiger is at the same side in here, so the probability of n observations, uppercase O, and the new observation, here left, here right, lowercase o, well, this product of conditional probabilities is, by definition of conditional independence, the probability of the set of past observations and the new observation. And in here we have the same, but tiger left, you know, tiger did not switch side, so the product of the conditional probabilities is, by definition of conditional independence, the conditional probability of the joint event given by the past history plus the single new roaring event. So at the end, under the conditional independence assumption, we indeed proved that what we obtained is the posterior probability given the n+1 observations and the prior without hearing any roaring belief b, and of course 1 minus b, my belief on the left side. So this means that indeed recursive evaluation one by one of the Bayes formula will give me the same result as a non-recursive evaluation with this conditional probability listening to m left and n right roaring events. So we can choose what to do. The thing is that, well, recursive evaluation is somehow intuitively appealing because, you know, I do not need to build a 100 rowing events conditional table with factorials, binomial, whatever. I just need to use 100 times the one rowing event conditional table we started with. And also, in many decision problems, for instance, I may be tempted to just apply one by one, and when I have enough evidence that tiger is at a given side, then I can escape through the other one. So let's say I don't know if I will need to listen for 5 roaring events or 26. I just apply recursively Bayes, 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 and when I am sure that 99.99% posterior probability tiger is left, then I escape through the right door. And in fact, that idea motivates the so-called recursive Bayes filters. It's important, so we will devote the next video of the case study to simulate that kind of situation and check that recursive and non-recursive versions of Bayes' formula give a coincident result. For the moment being, we end here. Thanks for watching.